This is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. In this session, I am going to describe about transformer coupled amplifier. This is one of the kind of multi-stage amplifier. So while coming to the contents, I am going to discuss about what is meant by transformer coupled amplifier and the analysis part of transformer coupled amplifier in order to find the voltage gain, current gain, input impedance as well as output impedance of the amplifier circuit. If we are comparing it with the single amplifier or single stage amplifier, how much gain quantity is improving and how much input as well as output impedances are improving in the case of a transformer coupled amplifier, we are going to discuss now. And also along with this, we are going to see the frequency response of transformer coupled amplifier during different frequency range of signals. That is nothing but at low frequency signals, what is the response, and at high frequency signals as well as for the mid frequency range of signals, how the gain is varying. According to that, how the response is varying, we're going to see here. So the frequency response of the amplifier is depends upon the different types of capacitors which are present in the circuit. So before going to the analysis part of the amplifier, first of all, we have to know what is meant by transformer coupling and what are the elements we are going to utilize for the transformer coupling here. See, actually why we are moving for this transformer coupled amplifier here. In the case of RC coupled amplifier, we observe that the drawback is effective resistance problem or effective load resistance problem here. That is nothing but effective load resistance is reducing here. So because of that, the input impedance of the amplifier is becoming low as well as output impedance is becoming high. But in order to get the faithful amplification from the amplified circuit, the input impedance should be high and the output impedance should be low. But because of the effective load impedance problem or effective load resistance reduction problem, in the case of RC coupled amplifier, the resistance, the input resistance is decreasing and the output resistance is increasing. So in order to overcome this, we are utilizing the transformer instead of resistor and capacitor components here. So suppose if we use the RC coupled amplifier to make the multi-stage amplifier by using the RC coupling with the low impedance, the output impedance of the next stage is coming parallel with the input impedance of the next stage. So overall the effective load impedance is decreased here. So this particular effective load impedance problem is overcome by the transformer coupled amplifier here. So in the case of transformer coupled amplifier, instead of resistor and capacitor, we are utilizing transformer as a coupling element between the stages from the first stage to next stage. So generally, in the case of multi-stage amplifiers, we are having different couplings. We can do direct coupling or resistor capacitor coupling or else transformer coupling. In the last session, we discussed about the RC coupled amplifier and the analysis of the RC coupled amplifier and also the frequency response of the RC coupled amplifier between different frequency range of signals. And also we have seen the frequency response of the RC coupled amplifier and we discussed the cutoff frequencies of the RC coupled amplifier. So that particular RC coupled amplifier is providing high amplification for the low frequency signals. For audio frequency signals, it is not providing the faithful amplification due to the effective load resistance problem. So in order to overcome that, only we are moving for the transformer coupling here. So what is mean by this transformer coupling here? So if we use between two stages of multi-stage amplifier, if we use transformer as a coupling element, so that we can call it as the transformer coupling. So here we are not at all using any capacitors in the circuit for coupling here. Why? Because the transformer itself provide the AC signal from the input to the base of the transistor. So directly base of the second stage of the transistor, the transformer itself providing. So that's why we are not at all utilizing the extra coupling capacitor in the case of transformer coupling. And the secondary winding of the transformer provides a base return path. So there is no need of any base resistance. Also, we are not providing any extra base resistance also in the case of transformer coupling. And why we are preferring this transformer coupling here means, if we use this transformer coupling, we can able to provide the impedance matching between two stages, and the overall efficiency of the system is also increasing here. So because of that reasons, most of the cases will prefer the transformer coupling here. And instead of utilizing two components, by using single element or a single transformer, we can able to interconnect multiple stages to make the multi-stage amplifier here. So here the transformer coupled amplifier is nothing but the amplifier in which the previous stage is connected to the next stage using coupling transformer is called as transformer coupled amplifier. So before going to this, we'll see the construction of the transformer coupled amplifier. So here I'm going to construct the two-stage transformer coupled amplifier. So in order to construct the two-stage transformer coupled amplifier, we require two transistors here. So I'm taking the two transistors. So this is the base terminal of the transistor, and this is the collector terminal of the transistor, and this is the emitter terminal of the transistor. So for the emitter terminal, we are having the emitter resistor as well as the emitter bypass capacitor C. Okay, so in order to provide the biasing for this amplifier circuit, I am utilizing the voltage divider biasing. So that's why I'm adding for the base of the amplifier, I'm adding two resistors. Those are R1 and R2. Okay, those are R1 and R2 here. So input signal we are providing for the amplifier through the capacitor Cin with the source resistance Rs. And my input signal is V in. These all terminals are grounded here. So for the collector terminal, we are providing the supply voltage VCC. So this is the single stage amplifier. Till now it is the single stage amplifier. So same kind of amplifier, one more stage I am taking here. So after taking that, to interconnect the two stages, we will include the transformer. So I am taking one more transistor. So this one I am calling it as Q1 and this one as Q2. This is the first stage and this one is the second stage. And again for the emitter, we are having the emitter resistor as well as the capacitor C. And to provide the biasing, again we are utilizing the voltage divider biasing here. So these are also connected to supply VCC. So these are R3 and R4 potential divider circuit. See here, in the place of collector also we are not utilizing any resistor here. So the transformer primary itself provides the required collector resistance here. So the secondary of the transformer or secondary winding of the transformer, the first secondary winding of the transformer is connected to the potential divider circuit, and the second end of the secondary winding is connecting directly to the base terminal of the transistor here. Okay, base terminal of the transistor here. So the transformer itself is coupling the output signal from the collector of the first stage to the base of the next stage here. We are not including any capacitor in order to pass the output AC signal to the input of the next stage. And again, across the second stage, we need to take the output. So again, for the collector of the second stage, we need to connect the primary winding of the transformer, and across the secondary winding of the transformer, we will take the output, that is V0. So this is the circuit for transformer coupled amplifier. Okay, this is a circuit for transformer coupled amplifier. So this is the first stage, and this one is the second stage. So this is about the construction of the transformer coupled amplifier here. So now we will see the function of each and every component in the circuit. So first, Vin is nothing but the applied input signal. Always we will take it as the sinusoidal signal with some frequency and some amplitude. We will fix some frequency, some 1 kHz or 10 kHz something, and we have to fix the input amplitude as some 5 volts peak to peak or 2 volts peak to peak. So that is our input voltage with respect to frequency. Okay, with respect to frequency or time period we have to take here. So this particular input signal through the resistance Rs, we are sending to the base of the first transistor Q1. So how this signal is passed into the base means by using input capacitor C here. So the function of the capacitor here, it allows the AC signals, okay, allows the AC signals and blocks the DC signals. That is nothing but if any DC content which is present in our applied input signal, that is blocked by this input capacitor, and only AC signal is passing to the base of the transistor. Okay, so that is the basic function of the input capacitor C in here. And while coming to this R1 and R2 resistors, so this R1 and R2 resistors are formed like a potential divider here. So this potential divider circuit is utilized to provide the stabilization as well as proper biasing for the amplifier circuit. So that is the function of both the R1 and R2 resistors here. And for the collector terminal, we are connecting the primary winding of the transformer here. So the collector resistance, the required collector resistance for the transistor is providing by the primary winding of the transformer itself. And for the emitter, we are connecting the emitter bypass resistor as well as emitter bypass capacitor. So the function of the emitter bypass capacitor here is it will provide the path for the amplified signal. Okay, what is the output signal we are getting from the circuit? It will provide the path for the circuit here. Okay, and the secondary winding of the transformer, the function of the secondary winding of the transformer here, it is to couple the output of the first stage. Though it is common emitter amplifier, the output we will take across the collector terminal of the amplifier. So across the collector terminal, we will get the output of the first stage. So the output of the first stage, we are connecting to the input of the second stage through the secondary winding of the transformer. Because of that reason, one end of the secondary winding we are connected to the potential divider network, and other end of the secondary winding we have directly connected to the base of the second stage or second transistor here. Again here, the function of R3 and R4 resistors are used to provide the proper biasing as well as in order to set the proper stabilization for the amplifier circuit. So, though we are not using any coupling capacitor in the case of output stage of the first one, the secondary winding itself will provide the output AC signal to the base of the next stage. So, this amplified output acts like an input for the second stage. Again, this amplifier will perform the amplification operation, and because of the mutual inductance between the primary and secondary windings, the output voltage will appear across the load resistor or else the secondary winding of the second stage transistor here. So here we will measure the output voltage V0. And again, the function of the emitter bypass capacitor should provide the path for the amplified signal here. So this is about the construction of the transformer coupled amplifier. So in that, first we discuss between two stages we are connecting the transformer in order to make it as a multi-stage amplifier. Okay, so the coupling transformer T1 is used to feed the output of first stage to the input of the second stage. Okay, and here the collector load is replaced by the primary winding of the transformer. I have already mentioned this also. And the secondary winding is connected between the potential divider circuit as well as base of second stage. So which is provides the input to the second stage. And instead of coupling capacitors in the case of RC coupled amplifier, we are using transformer as a coupling element here between any two stages. And the function of the potential divider network is to provide the biasing as well as stabilization. And emitter bypass capacitor offers low reactance part to the amplified signal, or error signal should be grounded. And the load resistance RL is used as the load impedance, and the input capacitor Cin is present at the initial stage of the amplifier. It will couple the AC signal to the base of the first transistor. So this is the circuit till now what we drawn in the previous slide. So this is the transformer coupled amplifier. Okay. So while coming to the operation of this transformer coupled amplifier, when we are applying the input signal through the capacitor C into the base of the amplifier, so once the transistor should operate as the amplifier, we should connect it in active region. So when we can get the active region operation of the transistor means when the emitter base junction is forward biased and collector emitter junction is reverse biased. So in that case, we can able to get the active region operation of the transistor. And along with that, we need to provide the proper biasing for the transistor. And along with that, we can also provide the proper operating point for the transistor. Once we fix the proper operating point only, the amplifier can able to provide the faithful amplified signal across the output. So that's why once when we wanted to operate the transistor as an amplifier, we should provide the proper biasing through the resistors, and we need to operate the transistor in the active region, and we need to set the proper stabilization of the circuit. So if we are providing these particular conditions for the two stages of the amplifier, in that conditions, when we apply our input signal, due to the amplification operation, our signal is amplified. The applied input signal will be amplified and appear across the collector or primary winding of the transformer of first stage here. So due to the mutual inductance between the primary winding as well as secondary winding of the transformer, this signal is passed to the secondary winding. The same signal will pass to the secondary winding of the transformer. So from this secondary winding of the transformer, it is connected to the base of the next stage. Again, in order to operate as proper amplifier in the second stage, again we need to provide the proper biasing using R1, R2 and RE resistors, and we have to provide the proper stabilization, and again we need to operate the transistor in the active region of operation. If we are making all that conditions to the second stage also, what is the input we are providing from the secondary winding of the transformer will pass to this base of the second transistor Q2, and it will also amplify again the signal, again it will be amplified and appeared across the collector of the second stage. And again, due to the mutual inductance between the primary and secondary winding, the same signal will appear across the secondary winding of the transformer, so that here we can connect our load resistor RL, and from this we can able to find the output voltage of the transformer here. So, what is the basic difference between the single stage amplifier and this two stage amplifier? Here it is. In the case of single stage amplifier, it will provide some amplification, and from that we will get the voltage gain AV, some voltage gain. But if we take the two stage amplifier, the voltage gain is multiplied by 2. Why? Because this particular stage 1 will give one voltage gain AV1, and second stage will also provide the voltage gain, that is AV2. So the overall voltage gain AV of transformer coupled is the multiplication of the gain of first stage and gain of second stage. So suppose the first stage it is 5 and second stage it is 5, means almost it is 25 in the two stage or multi-stage amplifier. But if you take the single stage, this value is 5. So almost in the case of two stage transformer coupled amplifier, the gain is becoming more compared to the single stage amplifier. So because of that reason, we are going for the multi-stage amplifier. And if you take single stage amplifier, we cannot able to run all kind of applications here. In order to run some applications, some practical applications, we require high voltage signals or high frequency signals. In that cases, we are going to utilize this multi-stage amplifiers. Okay. So I have already mentioned that when you are applying AC signal to the input of the base of first transistor, so that it is amplified and appeared across the collector terminal of the transistor, and from that it is connected already to the primary terminal of the transformer. Okay, so the transformer which is used as the coupling device in this circuit, it is having the property that impedance change. So which means that the low resistance of stage or second stage can be reflected as high resistance or high load resistance in the first stage. So always the low input impedance of the second stage will appear as high output impedance of the first stage. Okay, so because of this, the voltage of the primary is transferred according to the turns ratio of the secondary winding of the transformer here. So this transformer coupling will provide the perfect or good impedance matching between the stages of the amplifier. So generally we can prefer this transformer coupling in the power amplification. So in the case of a transformer coupling amplifier or any multi-stage amplifier, the final stage gain is unchanged here. And also, if we see the phase angle of the output voltage, generally if you take the single stage common emitter amplifier, output is in negative form. Why? Because output is 180 degrees out of phase with the input signal. But here we are using the two stages. So this negative voltage again we are applying, here it is, to the second stage, and at the second stage negative of negative you will get it as positive. So that's why for the 2 stage you will get always positive output and positive gain. And again for the 3rd stage it is negative. So for the even stages we will get the positive voltage and gain. For the R stages we will get negative voltage and negative. So now we will see the analysis of this transformer coupled amplifier. So till now we have seen the construction as well as operation of the transformer coupled amplifier. Now we will see the analysis of transformer coupled amplifier in order to find the current gain as well as voltage gain. Why we are going to find such parameters means we have to compare it with the single stage amplifier, whether that particular values are improved or not. See, physically we connected and we said that the gain is improving. Practically we need to prove that whether that gain is improving or not. So in order to do such analysis, we have to take the equivalent circuit of the transformer coupled amplifier. So how we can able to get the equivalent circuit of the transformer coupled amplifier? So the first thing here it is, we have to short all the capacitors which are present in the circuit. Okay, all the capacitors we have to short in the circuit, and also we have to short all DC sources which are present in the circuit. These are the 2 basic requirements in order to get the equivalent circuit. And after making these 2, we have to represent the transistor in terms of hybrid equivalent circuit. So after applying these 3 steps, we will get it as this equivalent circuit of the transformer coupled amplifier. So if we see our circuit here, so this is the circuit. So here we removed the CN and CE capacitor. Here also CE capacitor. So we removed all and we are shorting the supply voltage also. After removing all these, we are having except R1 and R2 resistors as well as transistor here and transformer here. And in the second stage also we are having R1 and R2 resistors and transistor QT here. So in order to draw the hybrid equivalent of the transistor, in the previous sessions we have already discussed how to draw the hybrid equivalent circuit of the transistor. By using 4 H parameters, we can able to draw the equivalent circuit of the transistor here. And again, while drawing the equivalent circuit of the common emitter configuration, here we will get in this way. So this is the HIE, HRE, VCE. This is the input side, and across the output side we are having the current source HFE, IB, and the admittance 1 by HO. And here it is input voltage, that is VBE, input current is IB, and the output voltage is VCE, and the output current is IC. So this is the hybrid equivalent circuit of the transistor by using hybrid parameter model. So this is the circuit for the exact analysis. Okay, this is the circuit for exact analysis. But here we are not using the exact analysis. We are moving for the approximate analysis. So what is mean by this approximate analysis here? So in the case of approximate analysis, we have to find first HOE into RL value from the circuit. So if this HOE into RL value is less than 0.1, then we have to move for this approximate analysis. If this particular condition is not satisfying, means we have to go always with the exact analysis. So here in the case of transformer coupled amplifier, I am going to taking here it as approximate analysis. So in the case of approximate analysis, these HRE, VCE as well as 1 by HOE terms will be removed. Why these particular terms we are removing from the hybrid equivalent circuit means, see, this 1 by HOE is in parallel with the load resistor. Load resistor will be present in the circuit. So if it is parallel with the load resistance RL, so this 1 by HOE value is high compared to RL. But if both the resistors are in parallel, which resistor is having less value, that is the result we will get. So RL only we will get. So RL only we are getting, that's why we are removing this 1 by HOE here. And similarly, in the case of input side, what is happening here? IC current is flowing here. Here I am taking HRE, VCE. VCE value, how we can calculate? VCE value is nothing but output voltage here. So output voltage, how we can calculate here? IC into RL, HRE into VCE equal to IC into RL. And what is my IC here? IC is nothing but again HFE into IB. So I am replacing IC with HFE into IB into RL. Suppose if we maintain our load resistance value is minimum or very less, at that time we can able to neglect these two values, HRE and HFE. But we cannot neglect the HFE here. Why? Because HFE is along with the base current IB. So that we can able to reduce the HRE VCE term. So that's why in the case of approximate model, we are removing this HRE and VCE. Only we are taking this HIE and HFE IB only. So that's why in the equivalent circuit, if we observe, so this is the circuit for the first stage. Okay, and this is the circuit for the second stage. It will be continued. The same circuit what is here there in the first stage will repeat in the second stage. But instead of taking this total exact model, I am replacing it with the approximate model. So that's why in the equivalent circuit of the transistor, I am including HIE1, the first stage input impedance HIE1. Okay, and also the current source HFE1 into IB1 and HOE1 here. So this is the equivalent circuit of the first stage. So between this first stage as well as in the second stage, the transformer is present. So that transformer we are representing in terms of turns here, N1 and N2. Okay, so the same stage again it will be repeating here. So in this way we can able to represent the equivalent circuit of the transformer. So from this equivalent circuit we can able to find the current gain of the transistor or current gain of the multi-stage amplifier. So in order to find that current gain, I am considering first the transformer ratio as K here. I am taking the parameter transformer turns ratio as K, that is equal to N2 by N1. And the turns ratio is equal to I1 by I2 if you take in terms of current. Suppose if you want to take it in terms of voltage means, we will get it as V2 by V1. But here we are not taking this particular relation. Why? Because here we wanted to calculate the current gain parameter first. Okay, current gain parameter first. So that's why K equal to N2 by N1 is equal to I1 by I2. And next we are taking the second stage input impedance is HIE2. Okay, this second stage input impedance is reflecting back to the first stage due to the impedance matching I have already mentioned. So HIE2 is reflecting back to the first stage. So once this input impedance of the second stage is reflecting back to the load resistance of the first stage, what will happen means the transformer turns ratio K reflects a load impedance Z to the primary. So once this impedance is reflecting back means along with that impedance, the turns ratio will also reflecting the impedance of the load impedance of the first stage. So that's why that one we are taking it as Z by K square, impedance divided by turns square. Okay, So after applying this particular condition, our input circuit or equivalent circuit will become like this. See, this overall circuit till here it is similar to the previous circuit only as it is. But the transformer we are replacing it with the HIE2 by K square. So this is the simplified equivalent circuit of the transformer coupled amplifier. Why we are representing with this particular term means the input impedance of the second stage is reflecting back to the load impedance of the first stage. In what terms it is reflecting means that is impedance by turns ratio square terms. So that's why impedance is nothing but HIE2 here and turns ratio is K here. So that's why HIE2 by K square. So from this circuit we have to find the gain now. So the output impedance of the first stage is HOE1 and the effective load transfer from the second stage is HIE2 by K square. So from the previous circuit we can able to tell this. Okay, for the maximum power transfer, between two stages, these two terms should be equal here. This output impedance of the first stage and the input impedance of the second stage should be equal here. So in order to make it as equal, I am taking here it as 1 by HOE1 is equal to HIE2 by K square. And what is my K here? N2 by N1. So substitute that K value here. If we substitute, we will get it as HIE2 divided by N2 by N1 whole square. So if we simplify this, we will get it as N1 by N2 whole square into HIE2. And from that, if we take only turns ratio, N1 by N2 equal to 1 by under root of HOE1 into HIE2. So that we can able to calculate the current gain in the mid frequency range of signals. Here we can calculate for the low frequency signals and for the high frequency signals as well as for the mid frequency range of signals. So for the mid frequency range, the turns ratio K is equal to the current in the first stage to the current in the second stage, I1 by I2. That is nothing but, I1 is nothing but the output current of the first stage, IC1, and I2 is nothing but the input current of the second stage, that is IB2. So from this we can write IB2 equal to IC1 divided by K. And again K is nothing but N2 by N1, but here K is in the denominator, so that's why we got it as N1 by N2 into IC1. So for matched conditions, the current, collector current IC1 through primary will be HFE IB1 divided by 2. From the equivalent circuit we can write. So if we write this IC1, if we substitute this IC1 in this expression, we will get it as N1 by N2 into HFE IB1 by 2. So that is the base current IB2. So the current gain from this is IB2 by IB1. If we take this IB1 term left side, we will get it as IB2 by IB1. That is equal to N1 by N2 into HFE1 divided by 2. So if we compare this current gain with the single stage amplifier current gain, this gain is very much high compared to the single stage or RC coupled amplifier. And next, if you want to find the voltage gain. So to find the voltage gain, we require the output voltage as well as the input voltage. So the output voltage is VC1 here. VC1 is nothing but IC1 into HOE1. HOE1 is nothing but what? K square into HIE2 from our assumption. So that's why we are taking here it as minus IC1 into K square is nothing but N1 by N2 whole square into HIE2. And from the circuit again IC1 is nothing but HFE1 IB1 divided by 2, and again IB1 is nothing but VB by HFE1. So if you substitute this IC1 value in the first equation, what we will get? VC1 equal to this value HFE 1 divided by 2 and IB1 is nothing but VB1 by HIE1 into this total term again here N1 by N2 whole square into HIE2. Okay. So from this, if we take this VB1 to the left side, we will get it as VC1 by VB1 is equal to minus HFE1 by 2 into N1 by N2 whole square into HIE by HIE2 by HIE1. So as per the transformer theory, the turns ratio N1 by N2 is equal to the VC1 by VB2. That is nothing but V2 by V1. So hence we can write it as minus N1 by N2 into VB2 by VB1 is equal to minus HFE by 2. Previous equation only, this total equation. Again we are writing right side as it is. So the voltage gain AV is nothing but VB2 output voltage by VB1 input voltage is equal to minus HFE by 2 into N1 by N2 into HIE2 divided by HIE1. Suppose if we take two identical transistors, means the input impedance of two identical transistors are equal. So if these two are equal means these two terms will get cancelled here. So the final voltage gain is HFE1 by 2 into N1 by N2. So this is the voltage gain. So this is the voltage gain and current gain in the mid-frequency range of signals in the transformer coupled amplifier. And similarly, if we find the low frequency response of the transformer coupled amplifier. So in the case of low frequency response of the transformer, we have to include the inductance of the primary winding of the transformer. Why? Because the reactance of the inductor is nothing but XL, that is equal to 2 pi FL. So the reactance of the inductor is directly proportional to the applied frequency here. So if the frequency is low means the reactance is low. If the frequency is high means the reactance is also high here. So that's why, because of it is proportional to the frequency, we are going to include the inductance of the primary winding in the analysis of the circuit. Okay. So that low frequency equivalent circuit is this one. This is similar to the previous circuit only. The only difference here it is we are including the primary inductance LP here. So this primary inductance LP is reflected from the secondary into the primary. So that's why we are shunting between the two stages. So at low frequencies, what will happen? The shunting effect of the inductance will be reduced. Why? Because frequency is less means the reactance is also less. So that's why the reactance also very less. So the effective load for the first transistor, due to which reduction in VC1 results in the reduction of the voltage gain. So next I am considering the impedance R, which is the parallel combination of 1 by HOE1. Okay, this 1 by HOE1 and HIE2, that is the next stage impedance. This one and this one are in parallel. So that's why that we are replacing it with a parallel combination of the two and that one with R. So two parallel combination resistances, we can write it as 1 by HOE1 into N1 by N2 whole square into second resistance, that is HIE2 divided by sum of two resistances. This is one resistance plus this is one more resistor. So here it is plus and this is one more resistance. So now if we find the cutoff frequency in this particular range, so cutoff frequency where we have to take where gain is maximum, that is suppose if it is 1. When the gain is falling from 1 to 0.707 times, at that time how much frequency is there, that one indicates the cutoff frequency. So in the cutoff frequency, the reactance of the inductor we have to include here. So that's why we are getting here it as 2 pi F1 LP is equal to R. And from that we can write F1 equal to R by 2 pi LP. So this is the cutoff frequency in the mid frequency range. And similarly, if you see the high frequency response of the transformer coupled amplifier. So in the case of high frequency response, the shunting effect of the LP at mid to high frequency is negligible. If the inductance of the primary winding we are not going to take in the case of high frequency signals. Why? Because if the frequency increases, the reactance of the inductor is also increases, so that it cannot able to accept the signal, so it cannot provide the high voltage, so that gain it cannot provide high. So that's why we are neglecting the effect of the LP here. But even though if we are neglecting the reactance of the LP, some leakage inductances as well as distributed capacitances in both the primary and secondary winding of the transformer must be included in the high frequency response of the transformer coupled amplifier. So that's why in the primary side we are including the LP, primary winding inductance, and CP, primary winding capacitance. And similarly in the secondary side, LS is the secondary inductance, CS is the secondary winding capacitance. So the high frequency equivalent circuit of the transformer coupled amplifier, when the load is connected to the secondary of transformer T1, is shown in the figure below. So here I am replacing this total impedances LP and LS with the L equivalent, and these two capacitors with the CP here. So the remaining circuit is as it is, N1 by N2 whole square into RL here. Why? Because again the second stage input impedance is reflecting back to the first stage load impedance. So from the equivalent circuit, we can write it as L equivalent equal to sum of the two inductances and C equivalent equal to sum of the two capacitances. So from this we can able to find the higher cutoff frequency F0 or F2, that is equal to 1 by 2 pi under root of L equivalent and C equivalent, where L equivalent is this much and C equivalent is this much. Why we are including these two inductance and capacitances effects means at high frequency range, the effect of these will be present in the response. So we have seen the response or analysis of the transformer coupled amplifier in the mid frequency range, in the low frequency range, as well as in the high frequency range. So now we will see the frequency response of the transformer coupled amplifier. So here actually what is meant by frequency response? So frequency response indicates the relationship between the voltage gain as well as frequency of the applied signal. So that's why we will take frequency versus voltage gain in dB as the frequency response. See here, suppose if we take it as the maximum gain AV and here it has 0.707 AV. So this one will indicate the F1, and where it is cutting in the high frequency range, this one will indicate as F2. So this 0 to F1 range is low frequency range, and this F1 to F2 range is mid frequency range, and from F2 to above frequencies are high frequency range of signals. So now we will see the frequency response in all the frequency ranges. So if you take low frequency range of signals, the gain is reducing here. Okay, in the case of low frequency signals, the gain is reducing here. So that's why it is in decreased form. So if we take the mid frequency range, almost we will take the constant, almost we will get the constant voltage gain. But if we take the high frequency range of signals, the gain is reducing. In some times the gain value will be increases here, but this increment is not our original signal because of the distortion added to our output signal, that is reflected as high in the frequency response. So this type of distortion we can call it as the frequency distortion. So that we can say transformer coupled amplifier is providing the frequency distortion in the case of high frequency range of signals. So it can be applicable for the audio frequency signals, and it will reduce the gain in the low frequency range of signals. So while coming to the advantages of transformer coupled amplifier, it is providing the excellent impedance matching between the stages, and it is providing the high gain, and there is no power loss between the collector and base resistors which are present in the transistors, and it is very efficient compared to the RC coupled amplifier or direct coupled amplifier. And while coming to the disadvantages of transformer coupled amplifier, even though it is providing gain is very high, but it is varying with the frequency here. So once the gain is varying with the frequency, so that's why frequency response is poor here. Why? Because frequency distortion we are getting in the high frequency range. So that's why that is the drawback of the transformer coupled amplifier. Okay, it provides the hum noise in the circuit, and it is very bulky and costly because of utilizing the transformer between the two stages. And while coming to the applications of the transformer coupled amplifier, most of the cases to provide the impedance matching between the two stages, we are going to utilize this transformer coupled amplifier, and mostly for power amplification. Why? Because gain is improving more compared to the RC coupled amplifier here. So that's why for power applications, we will utilize this. And wherever we require the maximum power transfer is required, in that cases also we can utilize the transformer coupling here. And in the case of RC coupled amplifier, we are not utilizing in the final stages. But this transformer coupled amplifier we can utilize for the final stages because of high gain from the transformer coupled amplifier. So in this session, we discussed about construction and operation of the transformer coupled amplifier and analysis of the transistor in all frequency ranges, and also the frequency response of the transformer coupled amplifier in low, medium and high frequency. And also we have derived the cutoff frequencies of the transformer coupled amplifier. And along with that, we have seen the advantages, disadvantages and applications of the transformer coupled amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.